Here is the central inconvenience of fusion. The thing you most need to know: the temperature, density, current, and magnetic shape deep inside a burning plasma is the thing you can least easily measure directly. Put a probe in the core, and it vaporizes in an instant. So we infer the inside from the outside, from the edges, and we do it well enough and fast enough to fly the machine. Everything starts with the diagnostics: magnetic coils ringing the vessel, interferometers counting electrons along a cord of light, spectrometers reading the plasma's glow, bolometers measuring radiated power. Each instrument gives a partial, noisy, indirect glimpse, never the whole picture, never quite where you want it, and always arriving with its own uncertainty attached. The goal is to turn that scattered constellation of glimpses into a single, complete, physically consistent state, a full map of the plasma everywhere inside, updated live. No one sensor can give you that. It has to be inferred, and that inference problem is exactly what state estimation solves. It is, in the end, a question of evidence. What plasma could have produced these readings? The first move is sensor fusion. No single instrument is trustworthy on its own, but together they constrain one another. A magnetic measurement, a density measurement, and a temperature measurement fuse through the physics that ties them together, agree on far more than any one of them could claim alone. The whole becomes sharper than the sum of its noisy parts. From that fused evidence, the twin reconstructs the plasma state, the internal profiles and the magnetic geometry that best explain everything the sensors are seeing at once. Not a rough sketch, but the specific configuration most consistent with all the data and all the physics simultaneously. It is the whole plasma, rebuilt from its edges, and refreshed fast enough that the reconstruction keeps pace with the real thing. The engine underneath is an idea borrowed from guidance and navigation, the Kalman filter. It works in 2 beats. Predict. Use the physics to say where the plasma should be a moment from now. Update. Pull that prediction toward the newest measurements, trusting each source in proportion to how reliable it is. Predict, update, predict, update, and the estimate tightens with every cycle. A plasma is deeply nonlinear, so we use the extended and unscented forms of the filter. Rather than pretend everything moves in straight lines, they track how the uncertainty itself bends and stretches as the plasma evolves. That is what keeps the estimate honest when the physics gets steep and the simple assumptions would otherwise break down. Step back, and this is data assimilation, the same discipline that powers modern weather forecasting. You never trust the simulation alone because it drifts from reality. You never trust the measurements alone because they are sparse and noisy. You fuse them continuously, letting each one correct the blind spots of the other, and the fused estimate beats either source by itself. For the breeder, the sharpest form of this is real-time equilibrium reconstruction. The twin solves the Grad-Shafranov equation live to find the nested flux surfaces, the true magnetic shape of the plasma, fast enough to hand that shape to the control system while it still matters. Offline, this calculation is a luxury measured in minutes. In the loop, we do it inside the control budget, and we check our own work. From the reconstructed state, the twin produces synthetic diagnostics. It predicts what each real instrument should be reading if the estimate is correct, and then compares against what they actually read. Agreement builds trust in the state. Disagreement points a finger at exactly which model or which sensor to question next. The estimator, in effect, grades itself in real time. Every number the estimator produces comes with an error bar, because a reconstruction without its uncertainty is a guess wearing a lab coat. Some of that uncertainty is irreducible sensor noise. Some of it is the model admitting where it is thin. And a word on status. This pipeline is validated in open simulation today. A conceptual design. Its calibration against real hardware begins at our first gate, G1, when estimate meets measurement for the first time. We publish the methods openly. That is the achievement underneath everything else Kronos does. We take a plasma that is, by its very nature, almost unmeasurable, and we make it observable, moment to moment, from the outside in. Every controller, every forecast, every safety decision downstream depends on it. You cannot control what you cannot see, and you cannot protect what you cannot control. State estimation is how we learn to see.